After work, you sit down on the couch to watch one episode of your favorite show. As the end credits appear, you realize it is now time to head to your study space and start working on class. To do this, you need to leave the couch, grab your computer from the table, get your coffee from the kitchen, and head to a different room. All of these voluntary movements take a great deal of processing by the brain. You must assess your surrounding environment and your body's location in it, determine which actions need to be completed, and then actually initiate those actions. In this chapter, we will focus on how the planning of voluntary movement occurs. Much of the cortex is actually involved in the planning of voluntary movement. Sensory information, particularly the dorsal stream of the visual and somatosensory pathways, are processed in the posterior parietal lobe, where visual, tactile, and proprioceptive information are integrated. Connections from the posterior parietal lobe are then sent to both the premotor regions and the prefrontal cortex. The prefrontal cortex, which is located in the front of the brain in the frontal lobe, plays an important role in higher-level cognitive functions like planning, critical thinking, and understanding the consequences of our behaviors. The premotor area lies just anterior to the primary motor cortex. This region helps plan and organize movement and makes decisions about which actions should be used for a situation. The premotor regions do send some axons directly to lower motor neurons in the spinal cord using the same pathways as the motor cortex. However, the premotor cortex also plays an important role in the planning of movement. 2 experimental designs have demonstrated this role. Monkeys were trained on a panel that had one set of lights in a row on top and one set of buttons that could also light up in a row on the bottom. The monkeys would watch for a top row light to turn on. This would indicate that within a few seconds, the button directly below would light up. When the button turned on, the monkeys were supposed to push the button. Therefore, there were 2 light triggers in the experiment. The first required no motor movement from the monkey, but did give the monkey information about where a motor movement would be needed in the near future. The second required the monkey to move to push the button. When no lights are lit, premotor neurons fire at a baseline rate, and the monkey does not move. Neurons located in the premotor cortex increase action potential firing rate when the top row light turns on, even though the monkey makes no movement. The firing stops shortly after the monkey moves to push the bottom button after it turns on. Therefore, when brain activity was measured during the study, neurons in the premotor cortex became active when the first light trigger turned on, well before any movement actually took place. In another experiment, people were trained to move their fingers in a specific pattern. Cerebral blood flow was then measured when they repeated the finger pattern and when they only imagined repeating the finger pattern. When the pattern was repeated, brain activity was seen in the primary motor cortex along with the premotor area and prefrontal cortex. When the pattern was only imagined and no finger movement took place, brain activity was still seen in the premotor area and prefrontal cortex. These studies show that the premotor cortex is active prior to the execution of movement, indicating that it plays an important role in the planning of movement. The posterior parietal, prefrontal, and premotor regions, though, also communicate with a subcortical region called the basal ganglia to fully construct the movement plan. The basal ganglia are covered in the next lesson.